All righty. Okay. Ooh, full screen. All right. Good evening, everyone. I'm Marjie Welchframe, and I am your host for this evening. We are delighted to have Dr. Mallory Thorp with us this evening. It's taken a number of months to actually get this to happen. We started planning this quite a few months ago, so it's really nice that now it's happening. Dr. Mallory Thorp began her astronomy career at the University of Washington, Seattle, where she obtained a Bachelor of Science, and at the DAO completed her first observing run. For the past 5 years, she has worked as a researcher and teaching assistant at the University of Victoria, where she obtained her PhD in astronomy last year. She has since moved to Bonn, Germany, where she is right now in the early morning hours, to join the Argländer Institut für Astronomie as a postdoctoral researcher. Please welcome Mallory Thorp.
Thank you, Margie, and thank you all for having me. It's really a pleasure to speak to this group. I've done activities for RASC, and it's always a delight, the enthusiasm you folks have. Let me just pull up my screen here. So today I'm going to give a sort of general talk on my extragalactic studies on what ends up fueling galactic powerhouses. By that, I mean hyper starbursty and hyper energetic galaxies. So I'm an extragalactic astronomer, which means I like to look at galaxies beyond the Milky Way. And that itself is a rather young science. It's only about 100 years now that we've known what galaxies are and how to go about studying them, which I think we often take that notion for granted, given astronomy is one of the oldest sciences in human history. There are astronomical stories and ideas that precede agriculture. And so over thousands of years, it's really just the very beginning of extragalactic studies overall and understanding galaxies as a structure in our world. And so if you'll bear with me, I like to take a step back, sort of my Astro 101 intro into what galaxies are and why we care. And to look into that, I like to use the Hubble Deep Field, which I'm sure many of you are familiar with, but just in case there's anyone who's a bit new to galaxy studies. The Hubble Deep Field was a project to use the Hubble Space Telescope to observe a blank space of sky, what I have here outlined in yellow. And it's surrounding what appears to be nothingness. No stars, no light, nothing inside those little squares. And just to give you a sense of how tiny this patch is, this is what the full moon looks like with respect to the Hubble Deep Field. So we're talking about a little pixel on the sky. And the idea was to observe this spot for a very long time, just to see what the image that came out would be. And we end up getting something that looks like this. And this is a truly phenomenal image. And it has all of these interesting little smudgy points in here. Every single speck of light, every single object you can see is a galaxy, which is a tricky thing to wrap your head around, right? Like these sort of nice oblong, eggy objects you can imagine as galaxies, but even those tiny little pixels. If you've ever been to University of Victoria, we have this image hanging in the stairwell to the 4th floor. And so as you walk up, you can look and see an exact single pixel of light and know that you're looking at a galaxy in the distant past. And so what extragalactic astronomers want to do is understand how all of these different galaxies relate to each other. Because you'll notice we're not looking at a bunch of Milky Way-like objects, right? There's a great diversity of behavior, of color, of shape, of size, of mass, and of greater properties if we can get into studying them. And so it was Edwin Hubble who sort of helped found this field of extragalactic astronomy, who proposed one of the first classification schemes, breaking galaxies into 2 possible types. Ellipticals on the left here, these sort of egg-like yellow, spheroidal, very old stellar population galaxies. And then more complex galaxies called spirals on the right, which tend to be disky and blue, and they have more substructure, things like spiral arms and bars, bulges and disks. And so Hubble suggested that there was this tuning fork, that the two galaxy properties sort of related to one another. You could go from an elliptical to something that had more of a disk or an arm until you got to an eventual spiral. We still use this scheme today. It's actually a very popular way to classify galaxies, but we now understand that galaxy structure is way more diverse than the Hubble tuning fork ever put out to. I love to use this image from the SING survey, which uses the Spitzer telescope to image nearby galaxies, because it's the same shape as the Hubble tuning fork with your ellipticals on your left. And as you move right, you go into these complex spiral structures. But using Spitzer, they've shown all of these different galaxies that fit in these classifications, such as the unbarred spirals and the barred spirals, and spirals that sort of lie somewhere in between. And you can see that our clear sort of transition between two galaxy properties is completely out the window once we consider the true diversity of galaxy populations. And furthermore, there's this class we call irregulars, which is basically where we throw every other galaxy that doesn't quite fit that scheme. And so they don't fit into our overall understanding of those galaxy classifications. And we're trying to understand why they don't fit into these very obvious subcategories. So as a result, extragalactic astronomers, we have a lot more in common with zoologists and marine biologists than your regular theoretical physicist. We don't set up experiments or conduct that kind of research. What we do is we go out into the field and we look at real objects and try and make connections between them all. Thankfully, we don't run into as much danger as those who have to study bears and sharks, for example, because our objects are so far away. Now, if most extragalactic astronomers are like biologists or zoologists, I'm that kid who's dissecting a frog. I don't want to just look at the object. I want to dive into it and try and understand what's going on in the internal mechanisms of a galaxy. Basically, what causes it to tick and what causes its structure to eventually form. And so through my work, I'm trying to understand how the constituents of a galaxy interact with each other to make them the way that they are. How do we see these forces at interplay between the material that composes the galaxy of gas and dust and stars, and often a central supermassive black hole? How do they relate to each other to create those different structures and properties that we see in the observed universe? And the main route to understand this is to look at something called the baryon cycle, which is how we understand how these three properties in a galaxy, gas, dust, and stars, relate to each other and cycle through phases. We've done a lot of this work in the Milky Way, where we have access to images of some of the first stellar nurseries. I have a picture here of the pillars of creation using the James Webb Space Telescope, which are these columns of dust and gas, which start to sort of centralize into these little nodules at top. And what we're seeing here is an in-process formation of the infant stars that will eventually become objects like our sun. Galaxies basically go through a feeding process where they take cold neutral gas sort of from their disk that they've pulled in from the circumgalactic medium. And over time, they feed on that gas. That gas condenses into very young, massive stars, bright blue objects that release a lot of light and a lot of energy. And that energy ends up impacting the gas in the interstellar medium, or what I'll call the ISM, to save myself time. And this energy input ends up changing the overall structure of the interstellar medium. I have this lovely image of the Bubble Nebula here, which shows you what happens when you have strong stellar winds off a Wolf-Rayet star. And as it impacts the interstellar medium, we see the properties of the gas change, which in turn can end up triggering new activity in star formation. And so we've been doing this mostly in the Milky Way because we have access to these highly resolved nebular studies. But that limits us in how we can study how galactic properties interact with those gaseous and star formation cycles. For example, in the Milky Way, we don't really have a fantastic sense of some of the global properties of the Milky Way because we're inside it. It's like trying to take a selfie, but we don't have a long enough selfie stick. It would have to be gigantic. We're sort of stuck on the inside, and it'd be like holding your phone out in front of you instead of just getting a nice image of your chin. You learn some things, but you end up missing out on a lot of the key details. And so we have to move outside of the Milky Way and study star-forming regions and external objects. So we could go to our closest neighbor and look at, say, the Andromeda Galaxy, because now we have a fantastic sense of the whole galactic properties. How do things like the disk structure and the bulge impact different star formation processes? But that is unfortunately just one galaxy. Now, if you'll remember, we've got a diversity of galaxy properties, right? All sorts of objects, all sorts of stellar populations, colors, masses. This is another image from the James Webb Space Telescope. And I remember folks on Twitter when it came out, everyone was picking their favorite. You would post about and say, oh, my favorite galaxy is this little pinkish one here around noon in the image. And so you can go through and pick each galaxy you like, pick your favorite, and you would hear a different story about star formation and gas. And so we have to move beyond both our Milky Way and single galaxy studies into larger surveys. So one thing we can do is we can just map as many galaxies as possible. And this is what we've done with the Sloan Digital Sky Survey, which over the last 2 decades has looked at about 8 million galaxies by basically observing the night sky every night and taking observations of all of the galaxies it can pick up with its camera. And using this, we've been able to really reconstruct the underlying structure of the universe. I have this fantastic map here of the Sloan Digital Sky Survey observations where each little point is a galaxy, and you can see the underlying structure of the cosmic web. This was a groundbreaking study. But again, if you're me, you want to dissect a galaxy. You don't want to see its broader structure. And we look with Sloan, we get some really nice images of galaxies, but they're subpar for the kind of interstellar physics we want to do. Right? We can see some factor of structure in these galaxies. We couldn't find individual nebulae turning gas into stars and to study that process. And so in the last 10 years or so, there has been a strong effort to make high resolution observations of local galaxies, such that we can understand the baryon process in our nearby universe, at least. And there's been a plethora of surveys that have done this. There's been the Vertigo survey, which is the image used here looking at the Virgo cluster. In this case, they made molecular gas maps of all of the galaxies in this nearby galaxy cluster to try and understand how factors like environment impact the gas structure. And you can see how even if these images were picking up on a bit more individualized gaseous properties within each of these galaxies. There's also projects like Edge Khalifa and AlmaQuest and SAMI. And I want to talk to you today about a collaboration I've recently joined called FANGS. The goal of FANGS is rather ambitious. It's to basically create a multi-wavelength survey of nearby galaxies that covers the entirety of the baryon cycle, from diffuse atomic gas, cold and across the galaxy disk, all the way to those hyper-energetic H2 regions and zones of stellar feedback from supernova. So the FANGS survey starts out by looking in the radio regime to map the diffuse atomic gas. That's sort of our base reservoir for star formation. And then moving to the submillimeter, they use the ALMA telescope to make CO maps of the dense molecular gas. You can basically do a nice solid conversion between that molecular line and the amount of molecular hydrogen gas in a galaxy. And they combine these two gaseous observations with observations in both space telescopes and optical telescopes, UV and infrared, looking at the star clusters and stellar population properties within these galaxies. So we can basically trace that reservoir of gas to the site of star formation, all the way to those new stars, and eventually to feedback from those stars, looking at H2 region ionization, stellar ejecta, and stellar winds using a variety of observatories. I'm going to focus for a little bit just on one galaxy, NGC 628, which was observed at FANGS. I have it on the left here, image of the Sloan Digital Sky Survey. And you'll already see that it's better than the other galaxy they showed because it's so much closer. We can actually pick up some really nice structure in the galaxy. And you'll notice these little bright spots as well of star formation. When it's observed at FANGS, we get just infinitely more information and a much higher resolution. So on the right, I have the same galaxy, But now each segment of this map is a different wavelength observed from FANGs. For instance, the ALMA CO measures the molecular gas structure in a galaxy, that region where stars are beginning to form. And now we have new observations from the James Webb Space Telescope, which help us probe both the dusty structure of the galaxy and the embedded star formation. And furthermore, we can combine this with observations from MUSE and HST, which give us information about the underlying stellar populations in the galaxy. And so by combining all of these factors, we can really understand the individual baryon processes happening within clouds in this galaxy, basically letting us do studies that we've done in the Milky Way for years, looking at individual nebulas, but for objects far beyond ourselves. And this has given us an unprecedented view on the way stellar feedback impacts the interstellar medium. So I want to focus just on the James Webb image because it's really made a groundbreaking step in our understanding of structure in galaxies, right? So here we have emission in the mid-infrared, which is often tracing the thermal dust emission of the galaxy. That's greatly oversimplifying things. And you can still see that underlying spiral structure first noted by folks like Hubble, right? We've got two sort of thicker arms coming off the galaxy and spiraling out in logarithmic spirals. But now we can also pick up on this really detailed substructure where there's all these little gaps in our dust emission. Some are quite small in the center. You can see these little itsy bitsy sort of holes in the dust emission. And others, as you go out to larger radii, are massive. And what we've realized is that these gaps in our dust maps are coming from the feedback processes of newly formed stars pushing out and interacting with the gas in a galaxy. So there was fantastic work done by Ashley Barnes to basically go through and map all of these different void regions, which it's shown here on the left where all of these circles are basically highlighting what they've considered to be a void in the dust map, which is easier said than done. By eye, your eye is quite good at going through and picking up what it thinks a feature is. We're fantastic pattern readers, humans. But they've had to train computers to do this, to really pick up on all the small structures. Because you can imagine if I gave you a piece of paper with this galaxy on it and told you to circle all of the holes you could see in the map, not only would that take you all day, but your eyes would be a little crossed at the end of it. And so computers are helping us sort of skip that extra step and apply a more statistical and repeatable identification process. But the work done by Barnes focused on one particular large void in this galaxy called the Phantom Void, which is a very, I feel, Star Wars-y-esque kind of name. I think it would make a good, creepy sci-fi movie. It's the biggest void in the galaxy, and it's zoomed in here on the right. It's about a kiloparsec in size. And what they noticed was some interesting behavior happening at the edge of this void. And for this, we need to take a step back and break down the colors in this image. So the James Webb data is mostly here in this sort of blue-gray color. That's tracing the polycyclic aromatic hydrocarbons. And then green color is tracing that general thermal dust emission. But they've overplot over the JWST image this orange color that comes from hydrogen alpha emission, which usually is triggered by gas being ionized by young massive stars. So if you see orange, you're not seeing young stars, but you're seeing gas that's surrounding young stars. It's a great way to pin down an H2 region, referred to as a hot ionized region of gas around a star that has very recently formed. And you'll notice on the right side of this figure here that there's this clustering of orange regions on the edge of the void. And what we've hypothesized is happening there is that there's emission from central stars in the void, that is moving out relatively quickly into the interstellar medium. And when it impacts the interstellar medium, there's a creation of new stars. Those shock fronts basically input energy into the medium, causing new stars to form. So we end up seeing this sort of bubbling feature. And this is easy to sort of trace when we look at this smaller precursor phantom void above our general phantom void. It's much smaller up here, but it's also got a much brighter and sort of more dominant H alpha emission. So what we're seeing there is the very first stars forming on the edge of that void. And they hypothesize that as the void grows, as feedback becomes larger and pushes into the interstellar medium, those stars begin to sort of age and sort of return to a more less ionized gas state. And then it can help and push the void out further itself, creating a sort of gradient of stellar populations. And this is now our understanding of how stars form in galactic structures, which means that observations have basically caught up to simulations. We've never really seen this before until the James Webb revealed the substructure to us, but simulations have been showing it for years. I'm going to show a simulation of a Milky Way-like disk forming in its gaseous component over time. You can see the time scale up here in the left-hand corner. As you can see here, our sort of pink strands are very dense, much more colder clumps of gas. And as the disk forms and they spiral into each other, you get that nice spiral structure of these flocculent arms forming. But you also can see these small little voids occurring, just like we see in the James Webb object. There's one that just popped up very frequently here. And if we turn our galaxy onto its side, we can see these voids are the result of gas being blown out by stellar feedback. You can see here these sort of chimneys of gaseous material bursting above the disk in the galaxy, because this isn't just a process that happens in the plane. It happens in a three-dimensional space that's sort of puffing up the galactic disk, despite how much more thin it is than the full disk structure. And so lots of simulations folk, when James Webb came out, said, well, it's good to see, observations finally catching up to the theoretical work, which is a cute sort of joke. But more importantly, it tells us that our theories of star formation are right, that these voids we see in galaxies aren't the result of our feedback models being too strong or dominant in our simulations, but that star formation is actually a bubbly process that is tightly linked to the underlying structure of the galaxy itself. And now, since I'm sort of at like a midway point, I want to pivot, because I've been talking about nice galactic structure, spiral arms, density voids. I'm more interested in what happens in a galaxy when things go cataclysmically wrong. I want to know what happens to the interstellar medium. Sorry, this video likes to keep playing. Once it undergoes an interaction with a second galaxy, basically taking that structure we've taken for granted and completely destroying it. So I'm going to play you a quick video here. And now, just to mess with you, I've changed to the stellar components of two galaxies instead of gas, because stellar components do a much better job capturing sort of structural change in a galaxy. So now we have the same model, right? The same sort of galactic disk structure I showed you in the previous video. But now we've doubled the simulation size, and we're throwing those two disks towards each other, just to see what physically happens when we start to have two objects gravitationally interact and how that impacts the overall structure of the galaxy. And when we let this interaction progress, you can see how we start to get behavior unlike anything else in the Hubble diagram. We have these strong spiral structures in the galaxy on the right, with these arms protruding sort of farther out than we would anticipate and flinging material away from the galaxy. And eventually we expect the two nuclei to coalesce, to become one. And as that happens, we get these strong asymmetric structures that both fling gaseous material away from the galaxy and cause it to lose angular momentum and be pulled in. And that creates this strong central burst of star formation activity. You can see all this blue and dark dusty lanes in the center of that galaxy. I'm going to zoom forward to it here to a quick second. There's a nice picture of it, right? Where our structure has been destroyed, and then we have these strong dust lanes and bursts of star formation, telling us that there's something different going on here than our overall understanding of the baryon cycle. right? We can understand little gaps and voids occurring in spiral arms, but how do we get such strong star formation activity in a galaxy when you take away that underlying structure? And we've seen this a little bit now with the James Webb Space Telescope, which has imaged Stephan's Quintet, which is a nearby interacting system of about 5 galaxies. And we can see this exchange of material and how crucial it is to the star formation process. So in the top right here, we have our 3 galaxies undergoing the most interaction. And this sort of white light is showing us the stellar structure, whereas the red light is showing you gas being sort of pulled between the 2 galaxies. And you can see these overdensities occurring between both. We sort of expect overdensities of gas to occur in both the center of the galaxy and in the spiral arms. But this is a case where we get overdensities outside of your classical galaxy structure. And you can see that they're often much brighter and denser than the gas structure in the bottom galaxy, which is sort of not quite interactive with the others yet. It's still relatively well behaved. Now that gaseous material can condense to form new stars, but can also be pulled into that companion galaxy. And as a result, turn on an active galactic nucleus, or what I'll call an AGN. You'll notice it in the top left corner here. It's got those lovely sketch marks that come from the James Webb Space Telescope, that 6-mark star. What we're seeing is a lot of emission in the mid-infrared, basically glowing amounts of emission. And that comes from new gas falling into the accretion disk around the central black hole within that galaxy. And that gas spins at a high speed and heats up and emits a huge amount of light. And this emission has a really drastic impact on the underlying interstellar medium. I think this picture of, I believe it's M87, does a fantastic job demonstrating just how extensive the effects of an AGN can be. On the left, we have an image of the black hole in the center of this galaxy. And you can see the heated up accretion disk around that sort of black point in the center where the black hole lies. And all of that emission ends up impacting the local medium in the galaxy. It can also lead to jets of material being shot out of the black hole. You can imagine it's sort of burping as material is consumed and pulled in, it's stochastically pushed out. And you can see that as we zoom out and look at the full galaxy image, where we have overplot here in X-ray, the jet coming off of this active galactic nucleus. And you can see little nodules of more behavior. That's those burps of activity. And that jet passes through the interstellar medium as it leaves the galaxy. It can both pull gaseous material away, but it also impacts the overall chemistry of the interstellar medium. It heats things up and can lead to greater reactions. Sort of like the stellar feedback we saw within our voids, but on a much grander scale. And so AGN are both something that occur on a very small local parsec scale. And they also occur over a full galaxy scale, impacting the overall gas reservoir of the galaxy. So we believe that AGN may be a crucial route through galaxy transformation, that they end up impacting the overall galaxy structure and tossing gaseous material away from the center of the galaxy and sort of starving a galaxy as a result, removing that gaseous material so it can no longer condense. And if not removing it, heating it so that it cannot cool down to form stars. It's counterintuitive because stars are hot, but you have to sort of imagine that gas, when it's diffuse, is nice and warm. And as it sort of is pulled in by gravity, it also has to cool down such that gravity can overcome that thermal pressure so that the first stars can form. And we've been using this process of either stopping star formation or starving galaxies to explain the star formation evolution of galaxies that we've noted in cosmic time. So I've plotted up here a very famous plot from Maddow and Dickinson 2014, which shows you the star formation density in the galaxy as a function, not in the galaxy, in the universe, as a function of redshift. So if you want the sort of layman's terms, on the y-axis, you have the amount of stars sort of forming per year per density of the universe. And on the x-axis, you have time. where 0 refers to the modern day and 8 refers to the very beginning of the universe. So the time axis here is kind of inverted, but that's because, astronomers, we love to invert variables. It's our great joy in life. And you can see that as we move from high redshift to low redshift, the star formation goes up. And that sort of makes sense. We can imagine a universe that begins with no stars in it. As it begins to form stars and more stars form and energy is input into the intergalactic and interstellar medium, we'd create more stars. But eventually at around redshift 2 or 10 billion years ago, this star formation activity peaks and then it starts to fall down. And astronomers are still trying to understand why there's this decline in recent star formation, in particular because it's also paired with a transformation in galactic structure. We tend to see lots of blue sort of disky galaxies at earlier times, and more recently we see lots of what we call red and dead galaxies, ellipticals with not a lot of gas, not a lot of new stars, and they're often in very tight clusters around each other. There's a lot of old galaxies sort of smashing around in a very dense environment. And so we think that AGN could be a fantastic process both for this morphological transformation from structured to unstructured, and also the star formation evolution from having a lot of new stars form to gas either being blown out or stopped at all from creating new stars. Now, my goal would be to try and see whether or not merger-triggered AGN have any impact on this process. However, it gets really tricky to study merger events and AGN in the real world because they're both transient and they both take quite a long time. I have here as sort of a joke, 2 galaxies interacting in real time. It's a video because taking an image and taking a video of these 2 galaxies is basically the same thing. You're not going to see any change in your lifetime. If you were paying close attention during the simulation of the interaction, you may have noticed that billions of years pass as an interaction progresses. And so we can never quite capture the full extent to which interactions change their constituents. And furthermore, any active galactic nuclei that are triggered by that interaction will be transient. They'll only exist for a very short amount of time during the interaction. So if we want to capture both the interaction and the AGN, we have to find a very specific point in time and try and reconstruct the merging process. Right? When we don't have access to a time variable and we can't turn back the clock, the best we can do is look at galaxies at different stages of interaction, both before and after they have an AGN as well, and try and piece back together how the full interaction process occurs. For example, looking at 2 galaxies that are clearly close to each other and about to interact, but structurally, they're very well behaved, so we know they haven't quite touched yet. 2 galaxies with clear connections between each other, telling us the interaction is occurring, to what I'll call post-coalescence or post-merger galaxies, where they're often irregular with these strong asymmetric structures, but we can only see one nucleus. And this is our most common phase to find the active galactic nuclei once coalescence has occurred. And so I end up doing a lot of work that's sort of like making a flip book, taking a lot of disparate pictures and putting them together to try and reconstruct a full process. But it can also be a little bit like being a conspiracy theorist, of trying to make connections between disparate objects that have no relation to each other. And this can have a lot of nasty assumptions in there. You might see a post-merger galaxy of an active galactic nuclei and assign objects that could be precursors that have nothing to do with it. And active galactic nuclei perhaps require other processes to form. And so it requires a lot of caveats and a lot of side eyes from simulations experts when you do this sort of work. But overall, my main research now is trying to use surveys to target these odd galaxies out, to look for unique objects like post-mergers and active galactic nuclei, and to understand how they impact the interstellar medium. And I've been doing this mainly with a survey called AlmaQuest, which uses the Atacama Large Millimeter Array in Chile to map the gas properties of these odd galaxies out, the ones that might not be targeted in your regular surveys of the local universe. AlmaQuest has only 2 observations to deal with, so we're taking a real step back from things. we only use integral field spectroscopy, which is optical data, and that tells us about the stars. And then CO emission to measure molecular gas using the ALMA telescope. And that tells us about the reservoir from which those stars form. And we've been using this survey to try and ask how mergers trigger starbursts within their galaxies, and whether or not we're seeing behavior that's distinct from that bursty information we saw in the FANGS James Webb image. And so I have an example interacting galaxy here, where the hexagon is showing you the integral field unit for the Apache Point Observatory using the MANGA survey, basically zooming in on that region of the galaxy and collecting optical data. And a sort of very simplified version of this is I've made this map where blue pixels tell you that there's a lot of new stars forming in that spot, more so than you might expect from the secular processes which convert gas into stars. And if they are red, you tend to have sort of normal or even less stars than expected. And on the right, we have this map of greens and pinks, green representing where there's an excess of fuel. There's sort of an expected ratio between the molecular gas and the stellar mass in any object. And we can use that ratio to help probe whether or not we have more gas than is expected in a galaxy, likely brought in from a companion, for example. And this is an interesting case where you can see the majority of the galaxy here is green. There's sort of a flush of gas across the galaxy's surface. But that doesn't correspond to new star formation. Right? You can see at the edges of this galaxy, sort of where the tidal forces are strongest, there's blue pixels indicating new stars forming. But the majority is red. And this tells us that the merging process doesn't necessarily create stars. It brings in the material to do so. But that creation of new stellar material is something that both takes time and takes those strong asymmetric structures. Now, I feel like I've sort of sold you guys short, and I'm showing you these nice pixely images. And if you're remembering the FANGS image, you're thinking this data kind of looks like poop in comparison, right? We were looking at a nice James Webb image earlier with phantom voids. I want to see that for merger galaxies. And it's something we're working on, but it's a very complex process to get to those FANGS images. It takes a lot of time observationally, and to justify that to a telescope committee can be quite tricky. And so we could use the FANGS survey, for example, to look at mergers or AGN. But of the 74 galaxies in FANGS, there are only about a dozen mergers. And that's because the mergers are ubiquitous. Every galaxy goes through multiple throughout its lifetimes. The event itself is relatively rare in our local universe. Only about 1 to 4% of galaxies are currently undergoing some stage of interaction. And if you can take a moment, I dare any of you to guess which galaxy in this image is currently undergoing an interaction. There is one merger. I'll give you a minute to think of it in your head. It's this one. It's 3627, which even by eye doesn't look particularly fantastical or post-mergery. It just happens to have a companion nearby. So we're not even sure if we're going to be capturing the effects of the interaction yet in a galaxy like this one. And so it's much better to have a targeted study than using something like FANGS, right? Going after specific mergers to recapture that process, right? Throwing out a dozen FANGS galaxies that may or may not be at the stages you want, you're going to end up not capturing the full merger process, how it impacts the interstellar medium. And so that's why we end up using AlmaQuest, because it about doubles the merger size. And these targets were chosen specifically for their merger stage. About half of the AlmaQuest targets are post-mergers, meaning that the interaction is finished up. And the other half are in the process of interacting, and it's evenly split between those on their first approach to nice structured objects, like say from the bottom two on the left here are sort of entering their first approach, while also having galaxies clearly deeply into the interaction, like on the far right, that object we were showing earlier. And so that allows us to have a complete picture of the merger process. And though we're currently in works to try and create a FANGS-like sample of mergers, that takes a lot of time on a telescope. And so using coarser resolution data allows us to collect more and make a telescope allocation committee happier by using their telescope time more efficiently, to sort of do these intensive statistical studies before diving in to the FANGS data. And so that's allowed us to understand how mergers trigger the birth of new stars. And you'll forgive me, I'm putting a very complex figure on here, but it's because I love to sort of test the boundaries on public talks and see what we can get through with a sort of more papery focused figure. I have each of the AlmaQuest merger galaxies here, and next to them, I have those maps of pixels I showed before. But now they're color-coded by whether or not there is an excess amount of molecular gas fueling star formation, and that is in this sort of brownish color, or if more stars are being created from the same amount of gas reservoir as you might expect without an interaction. And that's sort of this purple color. And this is helping us break down the two processes in a galaxy which create star formation. The purple you can imagine like that James Webb phantom void we're looking at. Feedback pushing against the gas that already exists and creating bursts of stars. Whereas the brown, that's unique to the merger event. That's material being brought in from a separate galaxy or pulled down from the galaxy itself by asymmetric structures to create new stars, irrelevant of how quickly those stars are being formed by stellar feedback processes. And what we see by looking at these maps sort of more generally is that all but two galaxies tend to have brown centers, and as you go out, things get purple. That means that things tend to be fuel-driven in the center of a galaxy, and on the outskirts, things are efficiency-driven. There are, of course, exceptions to this. Every galaxy is a bit of a snowflake. For example, you notice the two first galaxies are entirely driven by an enhanced efficiency at which gas is converted to stars. And there are also a handful where the entire galaxy is flush with molecular gas, most of these in the post-merger stage, meaning that their companion has sort of flushed the galaxy with new molecular gas material. But in general, we see this breakup between the central and extended star formation behavior in mergers, where in the center, gas is being pulled in by asymmetric structures, basically causing it to lose angular momentum and funnel into the center. And that either fuels a central starburst, like an AlmaQuest, but it can also fuel an active galactic nuclei. Whereas in the outskirts, more stars are being created due to these tidal forces, creating things like shocks and feedback, which lead to these extra bursts of star formation. And this is where we're sort of leading to a follow-up on this project, is to look at a handful of interacting galaxies in FANGS to see if on the outskirts of these galaxies, we can look for those enhanced voids sort of that we saw in NGC 628 and look for that bubbling star formation activity to see if that heightened efficiency is really driven on a sub-parsec scale, or if these structures are more driven by the sort of global properties of the interaction. And then lastly, I tease talk of active galactic nuclei, and that's because I'm on a bit of an advertising kick, because there's currently not a fantastic study of the resolved gas properties of active galactic nuclei. It's not out there. Myself, my collaborators, and more so my rivals also have been trying to look and get molecular gas maps for a broad set of AGN galaxies, because we would love to see if this sort of fuel-driven behavior we saw in the mergers, for example, if all of these galaxies would also trigger an active galactic nucleus. And furthermore, how that AGN ends up impacting both the local and global gas properties. Because there are some talks that AGN should probably deplete the gas reservoir around them. But in the one AGN we have in this merger set, this galaxy here on the left, the gas fraction actually stays relatively high, pulled in from that material. So we want to try and break down how merger-triggered AGN differ from their isolated counterparts. And so my work right now is focused on using the FANGS survey and the one AGN galaxy that is a merger in FANGS, NGC 3627, because it has fantastic maps from ALMA, from HST, and also from the James Webb Space Telescope to try and break down how the AGN is impacting that underlying structure in the interstellar medium. But unfortunately, I don't have any plots I can show you that today, and you'll just have to sort of look to future work. And our hope is that by studying this one galaxy and doing sort of a pilot study, we can hopefully convince people on telescope committees to give us time to do these sort of broader statistical studies like AlmaQuest, but for AGN, because it's a route through which the ISM could be altered that has yet to be sort of explored. And so I'll leave you with something to sort of look to in the future. And I think I'm at a good point now, maybe break and take questions.
David Payne.
Hi, thank you very much for a wonderful talk. I've always looked at the spiral galaxies as a vortex. And, in a vortex, the actual the shearing of the gases as it spins around the center is a lot higher in towards the middle than it is on the outside.
Mm-hmm.
And I'm wondering if it's that shearing that inhibits the efficiency of which the gas can coalesce and form new stars. And so when you get two galaxies interacting, it sort of breaks up that entire shearing system that's going on, and some gas finds itself in a more locally stable state and able to coalesce better.
That is an excellent point. That's the sort of level of a discussion section of a thesis for sure. I think it's tricky because when we talk about the center of the galaxy, we're also talking about sort of the maximum of the gravitational well. So even though there is greater shear, we've also pulled more material. And so this can kind of combat each other in a way, right? That you have more gas in the center than in the outskirts. And so the shear factor is sort of counteracted by there just being more material to form stars. But I think you're definitely onto something, that mergers disrupt that process. And without that central shear, things can go to sort of get kind of crazy. And I think that's to a good point why we see, I can pop back to it, so far away, structures like this, right?
Yeah.
Really strong star formation far away from the center because the gas is sort of like it's allowed to do whatever it wants. And so though I think it might be more complex than that. That's definitely a factor, particularly for the extended star formation.
I was just thinking of like the cigar galaxy with those where a lot of the gas is sort of outside the disk.
Mm-hmm.
And I guess a lot of star formation is taking place in that galaxy because of that. But anyways.
No, it's an excellent talk.
Thank you.
Thank you.
Gary, you have a question.
Yeah, so wow, excellent presentation, and you're a good presenter as well.
Thank you.
Glad to see smart young people like you. You mentioned when the galaxies were actually colliding, the AGNs were transient. I didn't understand your meaning of why they would be transient. I would have thought, like David was just saying a few minutes ago, that if these things are going through each other, there's going to be dust flying all over the place. So what makes it actually a transient phenomenon as they're going through each other?
You mean the merger event or the AGN event?
The merger, yeah, the merge. You said when they're merging, you made a comment about the AGNs of both of the galaxies being more transient. I didn't understand.
Yeah, no, that's because I skimmed over it a little bit, so that's my bad in part. When I say transient, I mean that it's something that sort of turns on and off, and this goes for both the star formation and the AGN, right? And we have galaxies interacting when they approach each other, and there's that first passage. You see a lot of activity, but then they fly by each other. And as they go farther away, there's some remnant of that information, but as time progresses, they sort of return to normal sometimes.
Okay.
And so even though time has progressed in the interaction, the effects of it are transient. And you see it sort of turning on and off as they come into each other. And
I see.
Yeah. Okay. And the same thing goes for an active galactic nucleus, both in the sense that at different points of the interaction, it will have enough fuel to sort of turn on. But also we've noticed in secular AGN that they appear to be sort of flickering on and off. They go through these behaviors of activity and non-activity, which we're still trying to understand. So I won't even go into that sort of theory. There are plenty of folks who study AGN and black holes in particular, and they argue a lot about why do they turn on and off? Why not just turn on at one point and keep going, especially when you have a really well-behaved disk continually feeding things. But that's a long-winded explanation of what I meant by transient.
Okay, good. Thanks.
I can see a hand waving and the portable.
Hi, you are a fabulous scientific storyteller.
Thank you.
But I want to tap into your inner conspiracy theorist
Perfect
mode and ask you what the range of futures for our Mother Earth may be, given the pending collision between Andromeda and the Milky Way, and maybe contrast it with our past fairly placid 4 billion years compared to what's in our future.
It's going to be absolutely cataclysmic. The Milky Way has been eating up a lot of satellites in its past, so this isn't the first interaction it's gone through. But Andromeda is definitely going to be the biggest thing we've smashed into for a while. And when that happens, we anticipate seeing an overall morphological evolution, right? Sometimes when we see interactions, they're small enough that they kind of like burst and sparkle and then go back to normal. Andromeda and Milky Way, based on our simulations, we're going to lose our gaseous disk structure and we're going to become a massive elliptical galaxy over time. Now, by that point, I believe the sun will have actually sort of faded to a white dwarf, so there won't be much for us to see. But we'll basically lose the band of the Milky Way and end up being sort of in this cloud of just old stars at the end of the day. And so thankfully, like simulations people care a lot about what happens to the Milky Way. So we have a really good sense that this is going to be one of the merger cases where things are absolutely blown out of proportion. I don't know yet if we're going to have an active galactic nucleus triggered, but given we're looking at a mass ratio of about 1-to-1, I'm willing to bet that we'd also see some really strong nuclear activity during the coalescence process. But yeah, the galaxy is going to look like a totally different animal in a couple of billion years. And it's a real shame we don't get to stick around to see it, because some of those merging stages in the intermediate are going to be really beautiful in the night sky.
I want us to stick around.
Me too. If we can get humanity to at least be in the Milky Way while it's smashing about, I think that could be some civilization goals. I'm not sure the biologists would agree with me, but I can be hopeful.
It's 2 billion years from now?
6 billion, I believe. Yeah, I think so. Don't quote me on that. I know we're recorded, but I'll put a little star on it.
Lauri.
Hi, Mallory. Thank you again for coming back and doing some more work for us here at the RASC. I was wondering if you could flip forward to that set of slides where you had all of the purple and brown sections. Yeah, that one right there. Okay. How do we know how big these are? Like, so I guess I can't tell just from looking at this, I can't tell whether or not, for instance, the one that is 1, 2, 3, the fourth one over on the top compared to, say, the one next door to it, the fifth one over to the top, like the one next door. What's the difference in size between those?
You should definitely be on thesis committees. I'm telling you right now, that was a fantastic, do you know your stuff question for sure. It comes down to both the survey structure, that's how I generally know, but there are also sort of physical mechanisms you can go for it. Basically, the MANGA survey, the IFU survey that makes this hexagon, is designed to target to about 1.5 effective radii. So basically, a good chunk of the stellar light. Now, physical size, like, kiloparsecs, That's going to vary galaxy per galaxy. And we can go through and determine that by basically taking the angular size of the galaxy. And then we also know its redshift. So we can do like a basic angle calculation. In general, the AlmaqQuest galaxies tend to range from about 10 kiloparsecs in size to 20 kiloparsecs in size. So you are going to see, like, the one you pointed out is definitely one of the larger cases. And you notice that a lot of the galaxies actually outside of the integral field unit. And so that is a bit of a problem we run into when we use massive surveys like this. But in general, we're not getting, beyond 20 kiloparsecs usually, or 30 kiloparsecs. 30 kiloparsecs would be a stretch with these galaxies. And so they're generally comparable enough. But it is something to consider when we talk about fuel versus efficiency. In these cases where we're at like a much further point from the center, we're going to see a lot more efficiency driven spaxels. Hope that answers.
Can you just back to that galaxy again, just right there where everything's on the outside and
Yes.
It doesn't look like there's anything in the middle, except there's obviously something in the middle, but we're not seeing that in your thing. So maybe I've lost something in the translation, but why are we not seeing anything in the middle?
It's because I skipped a step to show you pretty plots in time. We basically go in here and we have to measure accurate star formation, which is really tricky in the optical because basically hydrogen alpha emission can come from young stars. It can also come from shocks. It can also come from active galactic nuclei or things that look like active galactic nuclei, but actually aren't. We call those liars. And so we have to take out all of those pixels that have contribution from other properties to only the properties we know come from young stars. And so this galaxy here, I know for a fact that there's lots of old stars in the center, particularly a population called like A, G, and B star classifications. And those can create very similar hydrogen alpha emissions. So there is star formation in the center. We can't pull it apart from emission from old stars. And so to measure accurate star formation, we have to toss it out. The way to get around this is HST. You have a nice UV image, you have a complete stellar map, but unfortunately we don't have that for these galaxies. So they end up being kind of gappy.
Okay, thank you.
Thank you. Thank you.
Are there any other questions for Mallory?
Hi,
I think
that was wonderful. It's so much fun. Can you tell us how those galaxies all compare to the Milky Way in size and how far away they are?
Ooh, I'll admit I know my bounds, not every single one of them. Most of these are not Milky Way-like. In fact, they're usually a bit smaller, though not by like maybe 10, so like 10 to the 10 to 10 solar masses or so. So they tend to be around Milky Way-like or a bit tinier than that. Distance-wise, it's a range. We tend to be relatively close because we need to resolve the object. And so for that, we're pretty much bounded to a redshift of about 0.05. Anything beyond that, it tends to be kind of hard to see whether or not it's a merger. And then in terms of properties, we cover a much greater range of star formation rates. So the Milky Way is sort of a star-forming green valley galaxy. For those of you who know the nomenclature, it means it's, in the process of turning off star formation, but just at the beginning. And we cover a greater sort of range of properties from very starbursty galaxies to those which are like very close to the red and dead population. So overall, mass-wise, more similar to the Milky Way than they are in star formation properties. And distance-wise, relatively similar cosmologically. Is that good? Good. I sort of very answer to that.
Gary, you have a question.
Yeah, thanks, Mallory, for your answers there. I have a question for somebody else. I have a friend whose daughter, who's about 12, is interested in astronomy and engineering, but she's deathly afraid of being the only girl in the class. So could you give me something to tell her about how to get her some assurance that she's not going to be the only girl in the class?
Oh, that's tough. I remember being that girl sometimes. I guess I tell her that her people are out there And it just takes time. Sometimes you're the only girl in the room, and it can feel both intimidating and at times belittling. But if you are in enough rooms, you will find the other girls and the other non-binary pals, and even, some nice boys who are maybe a little less mean about things. And you find your people. And that's something it's why I do astronomy. Like, I was a physics major at one point, but in astronomy, I sort of found my people who liked to nerd out the way I do about space and wouldn't judge me for those sorts of things. And those involved women that I could really look up to over time. And so it's if you keep putting yourself in the room, you'll find them. But if you don't put yourself out there, you'll never be exposed. You'll never meet your people, your support network, the role models you want to see. And so, as terrible as it is, perseverance is sort of the way to go. And if it gets to be too hard, talk to some non-physicists and non-astronomers. There are lots of cool scientists out there doing other things who are also ladies who can help support you and make you feel less alone. That's for sure.
Good. Excellent answer. Thank you very much.
Really, really nice.
Yeah, I was just going to say that's a great answer. Just great. Yeah.
Yeah. Somebody in the portable has a hand.
That's me, Marjie.
Okay.
Oh, you were ahead of me, weren't you, Reg?
Yeah, I'm going to go first, if I may. Last summer, Mallory, I had the pleasure of driving you to the Island Star Party.
I remember.
I had a delightful talk with you there. And at that time, you had not defended your PhD. I think it was going to take place in November. And I just wanted to, first of all, congratulate you for your success in becoming a doctor. It's great news.
Thank you.
I've got one question, though. You showed a bell-shaped curve with the redshift on the x-axis.
I think I can remember where I put it. There we are. Yeah.
Okay. When we get out to redshift 3, 4, 5, and 6, with the new Hubble or James Webb Space Telescope is designed to see in the infrared, they're now detecting a lot more galaxies in the farther redshift area than they could detect with the Hubble because of the light shift. And that's caused quite a bit of controversy lately. And I was wondering if you have any thoughts on this. I know it's new. I don't want to put you on the spot, but what's your thinking on that?
No, I have thoughts, and you've picked a point where it's controversial. It's something that causes arguments over coffee and tea right now in the astronomy community about whether or not those results are real and dependable. I'm of the mind that I think it's a mix of both. I think we're probably seeing more star formation and more structure than we might expect. But I also am extremely skeptical of high redshift James Webb observations because I've read many papers about how the data reduction process can introduce massive error bars. And so a little tweak in the data, a little mistake, a little less noise correction can really drastically alter the galaxy properties. And so I'm kind of taking a step back and remaining skeptical for now because, right, it's new data against years of history. But history's changed before. And so this could be a restructuring of our understanding of cosmic star formation evolution. And honestly, if you want to hear more about it, there's a postdoc right now working at the University of Victoria called Leo Ferreira. And he does this exact sort of study. I think he actually recently published a paper looking at spiral structures in the high redshift universe of James Webb Space Telescope. And I've had many conversations with him where he's flipped from one to the other to being, yes, we're seeing an entirely new cosmic noon than we thought, to, no one's looking at James Webb data correctly. And it's actually all very in line with what we've seen before. And so honestly, I'd invite him out for a talk. He's a very smart gentleman, and he's really enthusiastic about this particular niche topic. And it's a fun controversy to get into. But for now, I'm remaining humble and skeptical about things and how we'll see our sort of view of the early universe change.
Okay, thanks so much. That's a great tip. We're trying to recruit new speakers, so we'll hunt out Leo and follow up with that. Thanks very much for your talk. It was great.
Thank you. No, I think he'd love to come present to you guys, though. I won't speak for him. I don't know if he likes public speaking or not.
Randy, you have a question.
Yeah, it's another community question. You talked at one point about your colleagues and your rivals, and my ears perked up with that. Can you talk a bit about the community that you are working within? Tell us something about the dynamic of the well, I don't know whether you want to talk about the astronomy community or about the extragalactic evolution community, but the word rival surprised me.
No, that's fair. And I think I like to throw out rivals because I like a little drama in my life, but the extragalactic community is actually quite collaborative in comparison. So, and this is hearsay, so now I'm spreading rumors, but in things like exoplanets and local star formation and supernova, there's a bit more competition between groups. Things can get a little bit more heated in a conference, whereas the extragalactic community, because we're so rabid for data, right? We're very, very young in the overall community. There's a lot of intergroup collaboration. But rivalries still form up because people get a sense of, well, I know the right way to collect this data. So, for example, I work with the AlmaQuest collaboration, and that was originally formed by two professors, Sarah Ellison, University of Victoria, and Li Wei Lin in Taipei, who were working on the same thing and kind of competing to publish papers about similar stuff. And eventually they got together and said, you know, let's pool our resources. Like, why not go out and collect as much data as possible and help each other out versus trying to do the same thing and competing for the same telescope time. And that's where rival comes from. It's all about that telescope time. We're all nice and friendly at a conference until we learn that such and such got 13 hours on ALMA and I got priority C time this year. And we go, my project would have been more easy. So rival is a soft word. In fact, now in the group I work with, I have an old rival of mine who's the other postdoc in the group. And so now we work together a lot and we end up collaborating on ideas despite often publishing papers that contradicted each other in the past. And so it's an amicable rivalry that I think leads to good things. But in an ideal world, we would all put in one proposal for each telescope together and no one would go out without data.
Thank you.
Are there any other questions? Yes, there's one in the portable.
Thank you so much for your...
You may have to come up towards the microphone.
Okay.
Yeah.
Thank you so much for your presentation. Very interesting. I'm just curious, just kind of moving forward in the progression forward in time, is it inevitable that all of the galaxies will eventually turn off in the sense of burning through all of their gas or through the destruction from the central supermassive black hole? Is it inevitable that they will all die, or is there some hope that there will be some galaxy life that continues?
I would say, and this is now I'm entering opinion land, yes, I believe it is inevitable. And that's simply because galaxies are converting that matter into energy, starving themselves basically, or causing it such that they can't sort of fall in anymore. And the way we understand the universe right now is that it's expanding at an accelerated rate. So merger events are going to get less common between galaxies farther away. We'll still have clusters interacting with each other, but those clusters will basically starve themselves of gas, creating stars that then become black holes. And that process will just continue until there's not any more gas to pull into the galaxy. There's not any new stars to form. And it's just a bunch of old dead galaxies and eventually more and more black holes forming as things become more separate and isolated, which is really dark in terms as an end to sort of the universe. But that's sort of what cosmology is showing us right now. So until someone can prove that we're actually in the case of a big crunch of things coming back together, I think matter is just going to keep getting further apart. Interactions will become less and gas will continue to be consumed. So a bit of a tragic fate for the universe in a way.
Thank you. I was hoping for a different answer. Thank
Oh,
you.
well, thank you. No, we definitely, astronomy can be a very dark subject considering we study so much light.
Are there further questions? Thank you very much, Mallory. That was it was a delightful talk. You have excellent slides. You were informative and fun, clear explanations. And I think of all the astronomy talks that I've heard in about 5 years, you are the only one that I have actually almost understood.
Well, thank you. That is the highest praise. And thank you all for a really fantastic discussion. This is my favorite thing to do. It's why I'm up at 5 a.m. doing it. It's a real delight.
Thank you so much. You're welcome to stay, of course, but you have other things I'm sure to do, but you're welcome to stay. We have a couple of discussions that are pending. And,
I'm afraid I must go because I do have to sleep for about 3 hours before I get up for work. So
good idea.
Check out. But thank you all for hosting me. It's been really delightful.
Thanks so much.
All right. Bye-bye, folks. Have a lovely rest of your evening.
So next on the agenda is Reg talking about the resumption of monthly meetings at Uvic, which will begin on October 11th.
Okay, thank you, Marjie. Joe Carr has done a beautiful job of putting together the information about the talk on the 11th. And I'm really excited about the speaker. Christian is the person in his PhD thesis in 2008 was the person who first photographed a picture of a planet or an image of a planet tracking around a star. And it generated a huge amount of interest then and has progressed thereafter. And he will be giving a talk on 3 different instruments that he's developing for the Subaru telescope and the Gemini North telescope to better measure even more detail about the motion of planets around stars. So it's going to be a terrific talk, and it's going to start at 7:30 p.m. at the Bob Wright Center in Uvic, and it's right across from parking lot number 1. And it's in room A104. And if you go to the victoria.rasc.ca website, all the information is there. And I urge people to come and hear this talk. I don't think it's going to be streamed, so it's for people who actually attend it. We possibly will record it and play it, put it on the web, but we're not certain of that. So if you want to hear this talk, I urge you to come out to Uvic. And after the talk, it's a tradition when we're at Uvic that we all go up to the 4th floor lounge of the Elliott Building, and we'll have cookies and coffee and conversation, and we can discuss and bounce ideas off each other. And also Alex will be opening up the library. We've got a beautiful library up there. Some people have just joined the club since COVID, so they've never seen this, and it's a great resource. So I really encourage you to come out. This is the first of several speakers that we're lining up for the fall and the spring of 2024. So stay tuned as we line up more speakers for you.
Thank you, Reg. And Lauri and David, you would like to talk about the annular eclipse on October the 14th at the DAO, Center of the Universe.
Hi, everybody. I can't see David in my list here, but I think he's there somewhere. Yes, we're going to be having, oh, there you are. we're going to be having a program up at the center. I think I said something a couple of weeks ago about this. We're going to be having kind of breakfast while we are looking at the eclipse up at the center. And we're planning for about 150 or so people to come up. And we're looking for where there's going to be a variety of options for people, of things that they can do up at the center. We'll have kids activities. We're going to have the planetarium open. We have got some wonderful, lovely little vignette talks by that Randy said that he was going to get ready. I think David has also got some things that he's planning. And David can talk to you a little bit more about where we're going to be and what we can see at the time. But what I'm hoping for is that possibly there'll be 5 or 6 different people from the RASC, maybe even more, that will be able to come up on that morning and help us out by putting out some of the solar telescopes that we've got, or bringing up their own if they have them. And also we will be giving out eclipse glasses to everybody that comes. So we'll need people to be helping with, how to use them properly, and helping anybody with that kind of thing as well. So I really would like to just kind of suggest to everybody that that's not the only thing that can happen on that day whatsoever. It is only one thing that we are doing. And that if other groups of people or individuals would like to go to different places in Victoria or out in the surrounding areas, and either put up a telescope or put up a sign saying, I have solar glasses, come and look at the sun for a little while, that there will be other people doing other things around, depending on where they live and what kind of thing that they would like to do. So in that regard, we have got solar glasses. They came, I think I said that last week, that I've got a box of them over here, which is just so lovely to see that everything came on time. And that in order to get them to different people, I'm definitely going to be at Uvic on the 11th of October on the Wednesday night. So I will be able to distribute any of the glasses to people who would like to have a few with, if they're going out somewhere else, we can give them out for sure. Or if you would like to, I'm going to have a good portion of them also up at the center. So this next week, between Tuesday and Friday, 10 to 3, the center is open for the public. So you can come on up, and if you're around in the area of the center, you can go in and pick up the glasses. I may not be there, but Amy Rawson will be there, and Calvin Schmidt will be there, and they can give you however many that you think that you would probably need. So in that way, we can get them sorted out. Also, if there's any of you there that would like to be a conduit for me, so that you'd like to take some of them, and then people say, if I could get somebody from, say, the Oak Bay area that could be a depot, or somebody in the Gordon Head area or something that could be it, then I might have to do a few drop-offs, but I don't have to do 25 drop-offs to different people, which is what I'm trying to actually gotta get away from. So if there's any other questions that anybody has, be happy to answer them. Tickets are going on sale next week.
Lauri, you mentioned that the center would be open on Friday. You meant Tuesday to Thursday, right?
Tuesday to Friday? Oh, is it not open? Oh, Friday's is the Easter weekend.
I don't know. I'm not sure.
Is that correct?
So.
I didn't even think about that. So let's just say Tuesday to yes, let's say Tuesday to Thursday then. Right?
So 3 days. 3 days.
Yeah, 3 days. So if anybody is interested in going up and getting it there, yeah. Okay, we're going to be charging for the public. Because we have to pay for commissionaires, we have to pay for the food that's being served. It's not a fundraiser. We're not trying to, get anything more. We're just trying to cover our costs. So I mean, donations are gladly accepted, of course, but we're trying to just kind of cover costs. So we're looking at approximately $4 to $5 a person to come up for a little bit of a snack and some activities and lovely talks and hopefully some sunny skies. Reg, don't even tell me that it's going to be cloudy. Okay. Although we do have plan B. It's okay. We have plan B.
Yeah, I think you should talk about plan B because
yes,
there are streaming sites that will
yes,
show the full annular eclipse
yeah.
along the path. And so it is rainproof because, well, I don't know, how many people can be in the auditorium at a time?
Oh, 70 or 80?
Okay.
Yeah, yeah.
But,
so
yeah, I'll either be talking inside or outside. And
yeah.
Are you going to be streaming it to the public?
We could probably put on the YouTube channel. Yes. So we could be streaming out the things that are in the auditorium. We can stream out on our YouTube channel. Yeah.
So actually in preparation for that day, I realized there's actually a beginners meeting this October 3rd, I guess. So I'm going to open up the beginners group to anybody, really. If they have any questions about using solar filters, maybe you may have purchased some film, then you're going to make a filter, or you're just not sure about how to go about safely using it, we'll field those questions on October 3rd.
And David, you did some preliminary work at where we'll be able to see this lovely sun.
Yeah, I did some work a couple of weeks ago just to see the trajectory of the sun. Now, obviously, it's going to be different on October 14th. I'm going to try to replicate that probably a few days before the 14th if I can. But it looks, based on all the software that I've used, it looks like Plaskett will likely obscure the eclipse if you're at the center of the universe, and trees will likely obscure a lot of it if you're on the other side of the Plaskett as well. But the best spot will be in the lower lot and where the machine shop is right now and where the new building is. There's not a lot of room down there, but people can just pass through. You're not going to be standing there through the whole 2 hours.
2 hours. No.
People are going to be passing through. I likely will set up there. If there's anybody else that wants to attempt to photograph it, more than welcome to join me.
Mm-hmm.
So even right in front of the 16-inch, won't the maximum be higher than the Plaskett dome?
I don't think so, but we'll have to try.
So. Yeah. Yeah. It may be at the very end. Like at the very end of it, it might be higher. But yeah. I think unfortunately the dome is going to be a little bit in the way that day. So we may be on the other side of the dome.
I'm going to test it. Hopefully maybe the day before or 2 days before. I'll have a better idea.
For everybody, for their own personal viewing, let's talk about what we're to expect on Saturday the 14th. So the sun will rise just north of east, I believe, and the eclipse will be starting right around 8:30, and it's at its maximum at about 10:30, I believe. Is that correct?
No, 9:17.
9:19.
Yeah.
It'll be finished at 10:30. That's it. And so you want to find a place with a good view, low elevation to the east. So Cattle Point would be excellent. Certainly Mount Ptolemy, Clover Point. What are some other good sites that people can suggest? But places
Island View,
where you have a nice, Island View Beach would be great.
Yep. They all have nice easterly
or Cordova
views.
Bay. Yeah.
Yeah. The most important part is an unobstructed horizon. I mean, there's no guarantee that the horizon line is going to be cloud free or mist free. So that's another challenge. But as I say, we've got till like 9/19 before the actual maximum eclipse. So yeah, I think it'll be okay. As long as it's clear that day, we should be all right.
And then for viewing, there's all manner of filters that will protect your eyes. One more
there's
time,
also
there's through your telescope straight at the sun.
Right. There's also projection as well. You can
is the most fun. You get a colander,
yeah.
Or you take there's a picture I just saw of a piece of cardboard, and somebody drew a heart and put a whole bunch of holes within that heart, and then you get this beautiful projection of all these little seeds, all these little suns with the bite out of it in the shape of a heart. It's very, it's good. Makes for a really nice photo.
Actually, I found a Life magazine article, I think out of the 50s or 60s, and they had a classroom where they took these giant cardboard boxes, and all the kids had them over their heads, and they had cut a little like an opening where they put foil in, and they poked a little pinhole in it, and they faced away from the sun, obviously, and they allowed the pinhole to cast an image of the sun onto the opposite side of the box that they could look at. It's quite a funny photo.
I just made one of those last week because we had a teacher's workshop with Mary Beth up on the Monday, and I made one, and the image was really small. Like if you just just put a small image, and I actually even tried to kind of change the size of them. It's really hard to get the right focal length, like to make it really work. And I found that just simply just a projection of something like a colander or something like a spatula with holes in it or anything like that at all was so much nicer than trying to do anything with a box. And
so the hole needs to be a little bit bigger. Now the other option is there's lots of plans on the internet where you can see people have taken their binoculars, and they basically project using one half of a binocular and project onto a screen, which actually has a cover on it. So there's options like that as well. I might try some of those anyways, just to share them with people so they there's other options.
Gary.
So about 20 years ago, I was up at the center of the universe, and this guy came along with a very unique device you solar folks should be aware of. It was a rotating disc that had sort of sandpaper on it, and it actually gave you a invisible light. This is the key: invisible light, the granular structure on the sun.
Interesting.
You know anything more about it?
I could try and find out if you like, but that's certainly a cool thing because you're not looking directly at the sun, but you got all the granularity there.
All the granularity there, yeah.
So I could try and find that if you like.
And we're open to just like if anybody's got any good resources, if you've got some links that you've really liked, that both like timeanddate.com and there's another one that's a really good one that simulates what the sky will look like. You can actually like put it out exactly as to what's going to happen and where it's going to be and that kind of thing. So, but the when you're doing it by projection, unless you've got something like one of our the bigger projectors that have got some lenses in them, they're very small. And so it's not like you're going to be able to see something that's like this big or anything like that at all. So you have to prepare people for that. But you'll be able to see the partial without any trouble. So we hope we do have a plan A for when it's nice and sunny, and plan B for if it's really mucky, and we're still going to be in the center and still going to be doing lots of things. So
I
hope
also
to have people come around.
I also wanted to say, not only are you going to see a bite out of the sun, I'm hoping there's going to be a fair bit of sunspot activity. So we should be able to see sunspots at the same time we see the obscuration.
If they're in the right place. Dorothy.
Sorry, a very good way to look at eclipses on to take a bowl or a bucket, fill it with water, make sure there's no wind going across it, and you get a wonderful view of the sun with a bite out of it. I did this up at Uvic one time some years ago, setting it inside a glass door so we didn't have any wind. And it for a partial eclipse. It was very effective, and that's simple to do. So just one other point while I have the stage here is that I wonder if anyone else saw the, excuse me, I think it was September 17th astronomy picture of the day. It's quite a wonderful one of shadows of the mountains on the moon. Worthwhile looking at, and some of you may remember I got very excited about seeing mountains on the moon from the 2017 solar eclipse. So that's something to look up. But the water surface is a wonderful, simple way of getting safely showing a lot of people, actually as many people as can stand around the bucket, what's happening with the eclipse.
I'm not sure how that works, Dorothy. Can you, or do you have a link?
You just put have the bowl or bucket of water where the sun can shine on it. And the sun was a bit higher than it'll be for this eclipse, the one at Uvic, but it wasn't too high.
Okay.
So
I just think it's going to be pretty low.
They're telescopes that are basically water surface.
Thanks.
I think the maximum altitude is under 30 degrees, actually.
So that's the max. That's probably about what the one at Uvic was, but that was just a lucky break. Engineering building, well, I guess it was there, but the trees weren't up. Sun wasn't higher than that, but it could have been 30.
Just fill the bucket up more.
Can I just ask a question about timing? I'm looking at one.
Mike, you muted yourself.
The time and date timings are what I've been using, but you can use any planetarium program. But I think it's 8:06 for the first bite, and I think 9:19 for the mid, and I think everything exits by 10:38.
Okay, I'm just looking at 135 on the Observer's Handbook at Victoria, BC for the 14th of October. And it says eclipse begins at 11:08. Max is at 12:20 and eclipse ends at 13:38. Is there
Eastern time, maybe? Look at the time zone.
No, it says that's Eastern. It says all times are local at the bottom.
Oh, local for where, though?
That's wrong.
Local for where, though? That's the thing.
No,
local for the person who's reading it? I don't know.
That's why.
Is that the 2020? Is that the 2023 handbook?
Yes, it is.
Oh my goodness. Okay. All right.
That's not good.
Right there.
Wrong. Yeah.
Okay.
No, go to time and date for Victoria. You'll get the right times.
Okay. There may be some people around who actually believe that this thing's correct, so they'll miss it.
Oh, could be. Brock.
Yeah, I just thought I'd share something that I did for the transit of Venus that worked really well.
Ah, right. So this is using a telescope.
Projecting, and you can see the trend. This wasn't for an eclipse, but the same thing would work perfectly well.
Brock, did you find that it heated up the tube at all, or were you worried about that?
It didn't cause any issues that I know of.
Okay.
I wouldn't use I wouldn't use a $900 Nagler eyepiece or something.
Yeah,
But,
so
Colossal or something.
Yeah, the recommendation is to use lens eyepieces that are not cemented. So a simple eyepiece is best, because what will happen is if it overheats, the elements might come apart.
Makes sense.
Yeah.
But it's
But that is one way to show a lot of people, like a lot of people can watch it all at the same time.
Yeah.
Because I think one of the things that we probably don't want to do all that much is have a lovely telescope and only one person can kind of, they're lining up to look through a telescope for only just a little tiny bit, right? But
I'm planning. If it's good weather, I'm planning to have a small screen that I can put the feed out of my camera into, and it's all battery operated, so people can look at that.
And we could potentially do that with the hydrogen alpha too.
Yeah.
Oh,
because
absolutely.
I did some imaging with the HA telescope after the Saanich Fair, and just tracking mount and having it hooked up to a monitor, and it actually, compared to everyone trying to look through the eyepiece, it would be in some ways nicer because you can actually see it better.
Well, Brock, I was hoping you were going to help out doing that.
Yeah.
Well, yeah, I would certainly.
If you can.
Yeah.
That would be great.
Bring a mono camera and a laptop.
I'm curious, if you use a telescope for projection, is it better to have an open Newtonian? Like if you were to use a Maxitov or Schmidt-Cassegrain, that would...
No, refractors
are... It has to be an open tube.
Well, no, refractors are probably the telescope of choice. With Newtonians and reflectors, you typically would have to construct an aperture anyways. Like you wouldn't want to have the whole thing open, right?
Yeah, but you have to filter on the...
You do, yeah.
You can't do projection with refractors. No, it's well, we've got that one that does actually set it up. Oh, really?
Yeah, I have it at my place. Okay.
Yeah.
Mm-hmm. Yeah, there's actually lots of people that have taken old refractors that are not fast, like are maybe like F10, F14 or something like that, and then they put kind of little funnel boxes at the back ends of them. In fact, I think that's how yours works, doesn't it, Alex? You have sort of a projection that comes off of the back of the refractor.
And then there's a screen on the back.
Right.
And then it's laminated. And then you adjust
the
and then focus on the screen. Okay. And then it goes through the front all the way through. Make sure you don't put your finger in front of
I was about to say, safety
that's
wise,
what
I
I
wouldn't want to be anywhere near it.
with my pencil sticks.
I guess.
Yeah.
Yeah.
Light on fire, yes. Very intense.
Yes.
Whatever.
This picture, if you guys can see that, was taken with the same method.
That's your screen, isn't it, Brock?
This is just a picture of that cardboard
of the screen, yeah.
Of the
That's
screen,
beautiful.
basically, right? And you can actually see mountains on the moon.
Yeah.
Yay, that's great.
And you can see the really
nice look at that.
Beautiful, yeah.
And that's just basically taking a picture. I think I used my iPhone to take a picture of what was being projected on the piece of paper. So pretty low tech.
Yeah. No end of solutions to this one.
Well, let me know, please, if you're interested in volunteering on the Saturday morning. We'd love to have you. Just throw me a line and you can do that. So just the one last thing before I leave here is I have put in an order for the calendars to the national. And I ordered 35. I kind of went in between, between 30 and 40. And if I know some people have already kind of given me, I want two, I want one, this kind of thing. So we'll put it out. I would think that it would take a little bit to get them anyway, but if you're interested in a calendar, again, shoot me a line of stuff just on roche.lauri@gmail.com and I will put you on a list.
You have mine?
Okay, thank you.
Yeah. I've got yours, Alex. Yeah.
Yep. You have mine too, probably.
Yeah, I have yours too.
Great. Thank you very much. Does anyone else have anything to share?
I could share a couple of images if you would like.
That would be lovely.
I think I can. Is that coming through?
Yes.
Yes.
Wow.
Beautiful.
This you might recognize as
David, you got to send it to APOD. Come on there, buddy.
I've sent a couple in and nothing came back, so maybe I will. This is it's a narrowband image of the lobster claw, and there's a cluster in here that's pushing out all the gases after being formed. Star cluster in here, and some other large stars that are influencing the shape of that, and that's creating one of those voids that we were talking about earlier. It's actually a cheat because I'm trying to take pictures of planetary nebula and supernova remnants this summer, and there is a planetary nebula in here, so I was justified in taking this image. And I'm just
what are the colors?
Zoom in it. The colors are the dominant in the whole image. The dominant is the hydrogen alpha spectral line that you capture with a hydrogen alpha filter, but where it is the strongest and overwhelming, you see yellow color. If you see red, it's more contribution of sulfur, and where there's blue, it's more contribution of oxygen. So this is a particularly colorful image. Move on to another one. Here's a planetary nebula known as the Shrimp Nebula, because I guess if you're looking at it with not so much background, just that curl seems to be a shrimp. And it's actually a moving planetary nebula, so it's not symmetrical. As you can see that on the tree, there's actually either the planetary nebula is moving through the media, or the media, which you can't really see, is blowing on the planetary nebula. But you see the gas is getting compressed and appearing very bright on the upper left, and all the radiation and gases in the interstellar media is kind of blowing apart the trailing edge. So it's like it's a planetary nebula in a windstorm. So somewhere in there, I think it's this star at these crosshairs, I don't know if you can see that, is where the white dwarf is for that animal. And I'll show one more. Oops, went the wrong way. I'll show one more that represents another popular subject, which is the Heart Nebula. And what I was actually after in this image was not necessarily the Heart Nebula, although it came through very nicely. But you can see all the dust in the background. This is another star forming region. But if you look on the right-hand side, you can see some wispy clouds around, which is actually a supernova remnant that you normally would miss if you're focusing on the heart, which is much, much brighter. So in the future, I'm going to just ignore the heart and see if, with more time on the telescope, whether I can get better definition on that supernova remnant. You can see a spherical sort of cloud after the supernova explosion.
Those are some pretty bright blue stars in there.
Yeah, those are actually, well, I have brought out the color, the saturation a little bit more, but they are blue. And you can see the blue around them. This is actually a reflection nebula. So it's not the nebula emitting. It's actually all this blue is reflecting, in this case, the light from this star. So reflection nebula tend to appear blue when you're imaging it.
Thank you, Dave.
Yeah, beautiful, David. When are we going to see your first dark matter image? You're doing
I'm not sure.
good stuff. Good.
I'm not sure I believe in dark matter, so.
So
it doesn't matter.
It doesn't matter. There you go. Good one, Marjie. Wow.
Great one, yeah.
Thank you very much. It's time to go. Thank you to everyone who participated and who showed up. As always, lovely to see you. And next week, are we back next week? No. Shaking of heads.
No. Good job hosting, Marjie.
The next Astro Cafe.
Yeah. Next Astro Cafe. 3 weeks. All right.
Got holidays on the next 2 Mondays.
Yeah.
Okay. Thanks, Marjie.
All right.
Thanks.
Take care, everyone.